All right, so now we've got these two Bellman operators, B1 and B2, that each one is associated with a fixed policy. So B1 makes an update essentially following pi 1, and B2 makes an update following pi 2. So we know a bunch of things about these updates. So, for example, we know that if we apply B1 to two value functions, what's going to happen to the value functions as a result?
They will not move further apart.
By a factor of at least gamma.
Unless they're the same one, right? If they're already perfectly together, then they won't move closer together.
Because they were at a fixed point. But then the distance is 0, and we do get gamma closer to 0 because 0 times gamma is still 0.
Sure. So that's true, but I'm just saying it's not that they always get closer together.
Yeah, okay. All right. That's fair.
Okay.
That's fair. If they're not on top of each other, then they get closer together.
Mm-hmm.
And the same thing is true of B2.
Yeah.
But there's some other interesting properties of these that aren't necessarily true of the standard Bellman operator, but they are true when we use a fixed policy like pi 1 or pi 2. So let's step through what some of those properties are, and we'll use them to show that policy iteration behaves itself.
Nice.
So this is the property that we want to show that B1 and B2 have. So if we've got two value functions, V1 and V2, not only if we apply these Bellman operators to them do they get no farther apart and actually potentially closer together, but they actually keep their same ordering. So let's say that V1 dominates V2. So V1 is bigger than or equal to V2 at all states S. Then that still is true after we've applied Bellman operator B2 or Bellman operator B1, but we're talking about B2 right now.
Okay, well, that makes sense, and I think it follows immediately from raising Thursday to the Monday power.
Oh, I see. No, that's supposed to be theorem. Sorry about that.
Oh, okay.
Yeah, we don't do day of the week math until the next section.
Oh, okay. Looking forward to that.
So how would we show something like this is true? The standard thing that we always seem to do is go back to the definitions and just plunk things through, and let's see what we get.
Okay.
To show that B2V1 dominates B2V2, I'll just subtract one from the other and see if the result is always non-negative.
Okay.
So let's do that. We plug in the definitions, and I did some canceling here because it always sort of comes out the same. This sort of notion that since we're talking about the same states and the same actions, these rewards are going to cancel. The gammas and the summations and the transition probabilities are going to factor out, and we're going to end up with something, well, actually a lot like this. Gamma times the sum over all states of the probability of reaching the next state times the difference at the new state S prime between the value functions V1 and V2.
Oh, okay.
And what do we know about this quantity here?
Well, we know that V1 is always greater than or equal to V2, which means that V1 minus V2 has to be non-negative.
Good. And then we take a convex combination of a bunch of non-negative values. There's no way it could become negative.
Right.
Could be 0, I guess. But we know that we're greater than or equal to 0. We can't be smaller than 0. So that gives us actually exactly what we need, that if V1 dominated V2 before, B2V1 dominates B2V2 now.
Nice. And that if we replaced B2 with B1, this would also be true.
Yes, exactly so. The only thing that we're actually using here is that we have a fixed policy. It doesn't matter what the policy is. So B1 and B2 are the same operators, except they just differ as to which fixed policy they're using.
Okay, so both B1 and B2 have mono. That's perfect.
No, they don't have mono. They are monotonic, meaning they preserve this kind of ordering property, not that they have mononucleosis, sometimes known as the kissing disease.
Well, maybe where you're from.